Okay, so I'm very pleased to be introducing our first Titan speaker today, Dr. Margaret Loper, who is at Georgia Tech. She has many titles. She's a principal research scientist at the Georgia Tech Research Institute, chief scientist, Information and Communications Laboratory. She's chief technical officer, Center for the Development and Application of IoT, Internet of Things technologies. Associate Director, Georgia Tech Institute for Information Security and Privacy. She's had 30 years of modeling and information experience, especially in parallel distributed systems. She's looked at issues like the interoperability of live, virtual, and constructive systems. She worked with the Department of Defense on issues related to HLA, high-level architecture compliance procedures, and Federation verification tools. She's looked at improving synchronization algorithms by exploiting temporal uncertainty. She was involved in the project for a modeling and simulation webbook, which is a search tool that can build an online library. In 2010, she was chosen as a 2010 Woman of the Year by Women in Technology. Her current research is in the area, which we'll be talking about today, of computational trust algorithms for machine-to-machine communications. So you can also view this talk today as a bit of a warm-up for the 2021 Winter Simulation Conference, where Margaret will be general chair, and the conference will focus on issues around interconnected smart cities. So without further ado, let's welcome Margaret to the stage.
Okay, I'm good. Hi, thank you, Peter, for inviting me to give this talk. Thank you, Rockwell, for sponsoring the Titans. Have always, when I come to WinterSim, I always love coming to these talks, and so it's a little intimidating to be on the stage today. But what I want to tell you about is some work that I have been doing over the last probably 7 or 8 years related to the Internet of Things and a topic called trust. And so what I'm going to tell you about is how that work kind of progressed and how it applies to the area of modeling and simulation. So as I was putting this talk together and writing the paper about this for the proceedings, I came across this quote, which I thought, it really connected with me, right? So the moral of this tale is that research is a long game. Patience and endurance are necessary components. And it really resonated with me because I didn't realize when I started to put kind of all these puzzle pieces together, all of a sudden realized how long I've been at this. But I guess many of us do that when we start to look back at things that we've done. So based on this quote, I decided that maybe the best way to tell this story was to use a timeline. So here we go. So I'm going to use this as a way to talk about the different work that's been accomplished over the years and try to bring it together at the very end. So I'm going to take you back in history a little bit to 1990. And so 1990 was a pivotal year in distributed simulation because it really was the beginning of formalized standards development for networking simulations together. And it was also the year that this concept called live virtual constructive, or LVC, was introduced to the simulation, the U.S. DoD defense community's vocabulary. And so some of you have probably heard LVC before, but I'll just give you kind of a brief introduction in case you haven't ever heard this before. So it's easily illustrated in this graphic here. And so what you see across the top is people, and along the side is systems, and then both people and systems can either be real or they can be simulated, okay? So the way it works is that if you have real people operating real systems for some simulated purpose, that's called a live simulation. An example of this would be like a training range or a test environment. If you have real people operating simulated systems, think about a human-in-the-loop flight simulator, driving simulator. This is called a virtual simulation. When you have simulated people or no people operating simulated systems, so you think about strategy simulations, war games, even CAD diagrams, right? So this would be called a constructive simulation. So in 1990, when this paradigm of how people and simulations interact was introduced, there was no concept that you would have simulated people operating real systems. And that's why we have a red question mark in the upper right-hand corner. So I'll come back to that. So as I said, this was 1990 was the year that kind of introduced more formal standards development. And this was done through a set of workshops. And the standards, the first standards that came out were called Distributed Interactive Simulation, or DIS. There was a series of workshops that were hosted to actually create these standards. And this became incredibly popular over the early 90s. And this shows you the attendance. These workshops were were twice a year. And so it became incredibly popular in terms of coming to these different workshops. The standards that we created were IEEE standards, and my role in this was actually, initially I was just a member of the community and the working groups creating the standards, but by the time I left, I was running the workshops, and I was actually the very first chair of the IEEE subcommittee that created the DIS standards. So then that takes us to 1992, and that was the first LVC DIS demonstration. So there is a conference that's hosted by the U.S. military that's called Inter-Service Industry Training Simulation and Education Conference. This conference in 1992 decided it would put on the very first demo of an LVC collection of simulations. And so we had 20 companies, 20 simulators, and one long-haul connection to an actual live tank on a range. So we actually really did have, on the floor, we had virtual and constructive simulations, and we had a live simulation coming in from outside. This is the exhibit floor. I know it's too small for you to see, but you know, there was a lot of companies that came together to actually make this happen. So it was very successful. It was very challenging because the first time you ever do something, it's always challenging. But it was very successful in that we were able to actually achieve this interoperability between these 20 different companies and their simulations. Our graphics back then were very basic, as you can see. And my role in this was then to actually, I was responsible for all the testing. So how do you actually bring those different simulations, LVC simulations, together and ensure some trust in the network that these things will work and trust in that they can communicate and exchange information. And the last piece of this little bit of history is that what we learned from the demonstration, what we learned from the DIS standards is that they were really well suited for only virtual simulations. They did work in a for constructive simulations, but they were really tailored towards virtual. And so there was this desire then by the US DoD to truly create standards that would address all of live, virtual, and constructive. And that is what started the high-level architecture initiatives. And so some of you in the room have probably heard of HLA and DIS. So there was a lot of things that I contributed to, both as a student working for Richard Fujimoto on developing time management, leading compliance and conformance testing and processes, and then supporting what was HLA's version of the LVC demonstrations called proto-federations. I also was a part of how you transition that whole standards process from those DIS workshops into a more formal organization called CISO that maybe some of you have heard of. Okay, so that is just a brief, where did I come from? And the reason that's important is because I spent a decade or more working in this LVC space, right? What are these LVC systems, standards, synchronization, testing? So we fast forward to 2012, and this is where the Internet of Things first appeared for me. So I know IoT, Internet of Things, is a common term now. So you've seen definitions. Some of you probably work in this space. So this is just a definition that I like from the European Research Council on the Internet of Things. And it goes like this. A dynamic IoT is a dynamic global network infrastructure that contains both physical and virtual things that have identities, that have personalities, use intelligent interfaces, and are seamlessly integrated into the information network, right? So we have virtual and physical things. And when I started to learn and read more about Internet of Things, what occurred to me is that IoT is just another LVC system, okay? So it just, the whole concept of virtual and physical things and how they interact, right? So IoT just becomes the interaction between people and things instead of people and simulations. And so I've recreated this quadrant here for you that I showed you on the previous page. So we have people along the top, systems along the side, and now we have real and virtual versus real and simulated. And this could be physical and virtual, right? We could decide what is the best conceptualization. But what you see is that I've taken an initial stab at what are real people operating real systems, right? These are sensors and devices and smartphones and security cameras. Real people operating virtual systems, so things like mobile apps and social media, navigation systems that we use all the time for driving. Virtual people operate, or no people, operating virtual systems. So this strikes me as this is all the massive data that we're collecting in these sensors and devices, right? So this is the analytics. This is the machine learning. These are the embedded systems that are associated with Internet of Things. And now we can actually start to name that upper right-hand quadrant, right? Because now there are virtual people operating real systems, right? So I've called it autonomy here. You may have another name that you'd like to use. But this is driverless vehicles, robots, home building automation, right? So there is a parallel. And this is one of the reasons that I gravitated to looking and being interested in Internet of Things research. I got excited about this, and my next challenge was to get the organization that I work for excited about this. And so what we did is in 2013, GTRI, the organization I work for, had an Internet of Things ideation event. And so an ideation event, for those of you who have not participated, is like a big brainstorming session, right? Sometimes you use tools to help mediate that, but usually it's about how you put ideas, get people to brainstorm and discuss ideas, and then be able to try to connect them, not in a structured way, but somehow to try to create structure out of that. And so our ideation event, we used a tool, and we had about, 300 people that participated in our ideation event. About a third of those were really active, as in it was over 3 days, so they were actively always engaged online, trying to generate ideas and build off other people's ideas. And then about 2/3 were more lurkers that were just throwing out ideas a little bit. But it was successful, and the questions that we asked people to ideate on are listed there. It had to do with products and services, technology gaps, and most importantly, what is Georgia Tech or GTRI's role in this space? So here along the left-hand side, that's a lot of words. I don't expect you to read those. But I will just say that we generated a lot of ideas about where GTRI or Georgia Tech can fit in this space. Right, we had the recognition that we are an applied research organization affiliated with the university. We are never going to compete with Facebook or Google or AT&T or IBM or Cisco or any of these major companies that are going to be owning and working in the Internet of Things space. So what can we do? What is our niche? And one of the things that kept popping up was this area of security and privacy. And so the organization that I work for is predominantly the work that we do is around national defense. And so so one of the questions that came up is, is IoT even important with respect to national defense and security? And so this quote comes from a report from the National Intelligence Council where they go on to say that individuals, businesses, and governments are unprepared for a possible future when internet nodes reside in everyday things, right? That while there are a lot of benefits that this technology will bring to society, there is also a lot of risk associated with having objects, so many objects that we can remotely control, locate, and monitor. And the reality is that IoT is a disruptive, and this was back in 2008, that IoT is a disruptive civil technology because IoT could distribute those risks far more widely than the internet has to date. Okay, so from my company perspective, there was a hitch there, right? Maybe the security privacy is an important area for us to look at with respect to looking at investing internal funding. So we basically came up with, out of all of this, a research niche for us, which is security, privacy, and trust. So the idea is that the resilience of IoT on simple, cheap, inter-networked processors has profound implications on security. The potentially invasive nature of the information gathered has implications on privacy. And the implicit reliance on technology to make decisions on our behalf, because that's what those IoT devices are doing in many cases, gives us this need to really think about how to express and reason about trust. So for a variety of reasons, we decided that our first foray into research in a more focused way, we were going to look at trust. So fast forward a couple of years, I've gotten my organization to really focus on funding internally some research in the space in the area of trust. So the first thing, of course, is what do we mean by trust, right? Because there's lots of, you say trust and everybody has their own interpretation. So there's lots of definitions of trust, which you probably would not be surprised to hear. Things like the competence of an entity to act dependably, securely, and reliably within a specified context. The extent to which one party is willing to depend on somebody or something in a given situation, even though negative consequences are possible. And the demonstrable likelihood that the system performs according to design behavior under any set of conditions as evidenced by characteristics including security, privacy, reliability, safety, and resilience. So it is this last definition by NIST that we ended up basically adopting. And the reason is because it represents trust as a very multidimensional concept, right? And so we know that in IoT has basically 3 modes of operation. That is human to human, where maybe some IoT devices is in between that human to human interaction. Human to machine, and machine to machine. So this is what the modes of operation that IoT provides you now. And so we need a definition of trust that basically encompasses all of those different dimensions. So we adopted this idea that trust it has got many dimensions, like as defined by NIST. Also, in this period of investigating definitions of trust, I read lots of articles, right? Like we always do in research, you go to the literature and start digging up conference and journal papers and trying to decide who's doing what in the space. And at first it became extremely confusing because I'm seeing trust all over the place. And then I came across this article that really kind of brought it into clear view. And it is that there's 2 types of trust research that have been published. There's the security-oriented trust, which adopts a very a restricted view. So it thinks about entities trust being an absolute property of an entity, right? So it either does or does not have it. It either is trustworthy or it is not trustworthy. It also, lots of the literature looks at the credentialing process and thinks about trust as enforcing certain hardware and software behaviors or through different encryption maybe techniques. Or that trust is determined through some type of formal verification process. And then the other side of the research that I found was this non-security oriented, which adopts a much wider view and similar to social sciences, right? So it's not a matter of whether it is or is not, black and white, whether it is or is not trustworthy. It's about, it is to a degree, right? That it's some measurable property that entities have in different types of degrees. That trust is determined based on evidence, maybe observations or experiences that you have, and that is situational. Context matters, and it also includes this notion of malicious and selfish behavior. So this idea that it's either security-oriented, non-security-oriented, really also kind of hit along this idea that these modes of operation in the Internet of Things. So at this point, I decided that it was important, read a lot of literature, needed to formalize a trust framework. And so I adopted this one. This is not one that I created. I pulled it from the literature because I think it really captured all of the ideas that I was struggling with. And it's really a layered approach. At the bottommost level of this physical perception layer, where we think about perceiving physical and human environment, we think about data perception trust. The sensing and collection process, is it reliable? What is the attributes of the sensors that are collecting that data? The persistence and security of the sensors, that type of thing. Another level up is the network layer. And so this is where all that data that is collected at the perception layer is transformed, right? It is communicated and transformed into something that can be used. And so different types of trust here, like how you mine and fuse the data, how you transmit and communicate that in a way that is only the entities that should get that information can. And then at the top level, the application layer is where this context-aware services appears, so how the humans interact with us, right? And then we can think about things like quality of service and human-computer interaction and what trust means there. And then, this idea that if you want to have a trustworthy system, Internet of Things system, you also think about how all of the trust across all of these layers works, right? So what this captured is this idea that there's lots of ways to compute trust and to look at trust at different layers of this layered model, and then how does that all work together? Okay, we have a definition of trust. We have a trust framework. So now I was ready to start into what kind of research, right? And so in the kind of next phase was to think about what are those initial projects that we were going to do. And so this was the going-in statement that I proposed for internally to get funding, and that is, what if you need to operate in an environment where you don't know if you can trust the sensors, devices, or machines, right? And when you think about the Internet of Things and these very open, dynamic, membership-changing environments, this is very possible. You don't know what devices are out there that you might interact with. So there's our trust framework. We had a little bit of an architecture that we created, thinking about sensors on the bottom. We have these aggregators at this network layer, the things that collect data from the sensors, that transform data, communicate data among each other, and of course, at the top level, this command and control or decision-making where humans come into the loop. So my first foray into this research is I was able to get 3 different projects, small projects funded, which occur at these different levels. So I'm going to tell you briefly about these because I'm going to bring this full closure at the end of the talk. Okay, so for the first project that we looked at was called Machine-to-Machine Trust. And this was how machines, when thinking about this aggregator, so that middle component there, it's collecting data from sensors, and then it has to do something with that data, and sometimes it's going to communicate data across the aggregators themselves. So how do those things know how to trust each other, right? So this was work collaboratively with a professor at Georgia Tech, where we looked at reputation systems, right? So how you interact, how these nodes interact with each other, and they rate each other based on their services. So our approach was separating the transaction performance from the rating performance. We used a self-driving vehicle scenario. And the important thing about this was it was not just an algorithm development. We really spent a lot of time looking at attack models, right? How malicious nodes in an Internet of Things environment may want to attack and change, persuade, influence, right? How these nodes communicate and what information they communicate. So our work did that. We looked at 4 or 5 different attack models, things like collusion and camouflage. And the short version is that our approach, M2M trust model, compared against the seminal work at the time, which was called Eigentrust, was more resilient to these threats and malicious attacks in an IoT system. The next project, also at that aggregator level, was called a trust negotiation language using something called trust marks. So in my laboratory, there was a group of people that were doing a project for NIST called Trust Marks. And it was about how you actually look at a concrete set of requirements and do some kind of certification of that that can be exchanged in enterprise systems. And so we took the work that they'd done in trust marks and then applied it into this IoT environment to make it more computational. And so the example is that if Samsung created a smartphone with a particular Android capability, then Android could grant a trust mark to Samsung on that capability, right? That it had been tested, that it is approved, and that it operates in a way that is expected by Android. Then Samsung could deploy those trust marks on its phones, and there would be this understanding that if you were going to exchange that type of information, that there was trust associated with what that data was and how it was produced and used. And then the last project that we did was at the perception layer, the lowest level, and it was on device trust and sensor arrays. And so the idea behind this project was that in Internet of Things, we are deploying sensors everywhere, right? And we are creating sensor arrays, so arrays of 6, 10, a dozen, sensors in a box that you put on a lamppost, for example, that can monitor all types of things. Maybe it's pollution, weather, traffic, pedestrian. And so the focus of this work was to look at security by design, building in security into these types of devices, and also to actually do privacy, create privacy algorithms that could be used in situ in these boxes, so that instead of taking all the data from the sensors and pushing it back to the cloud to be analyzed and then pushing an answer back to the sensor array, that you could actually do the analytics in place, but preserve the privacy, for example, of the pedestrians, if you were doing pedestrian counting, that you did not violate the privacy of the people on the street that were being sensed. So at this time, there was also, Peter mentioned in the introduction, my association with Georgia Tech's IoT Center, SEDATE, as well as the Institute for Information Security and Privacy. So 2 organizations on the Georgia Tech campus. Both the SEDATE Center, the IoT Center, has a focus on security and privacy, so I've always worked through them with respect to the trust work that I was doing. And then with IISP, they actually have 6 different research focus areas, and trust is one of those areas, which is how I became an associate director there, and have ended up doing, and I will tell you about some research that I did through ISP with a faculty member there. Okay, so that was the introduction to really doing some trust research. So the next, fast forward a couple of years, and we start to expand that research and look at other things like smart cities. So no need also to tell you about smart cities. I'm sure you're very familiar with this because many of your cities are right in the middle of deploying this technology. But this was kind of at the early onset within the U.S., not abroad. They were far more advanced than the U.S. But in the U.S., cities were kind of latecomers to smart city technology. So what I've listed here is there's lots of commercial smart city technology out there, far more than's listed here, but things like smart waste collection, trash bins that can tell you when they're full and they need to be emptied, public safety, so video cameras, license plate readers, gunshot detectors, efficient buildings, so occupancy, HVAC, lighting, right, how to make the buildings more self-sufficient and aware, transportation, how to find a parking spot, how to navigate to that parking spot, where the available charging stations, Wi-Fi kiosk, things that many cities are deploying to help people navigate downtown, find maybe from a tourist perspective, where things are that they might want to see, or where transportation alternatives are, maybe announcements about weather or other upcoming events, and also smart street lights. So this is that idea that you're going to connect sensors to lampposts, which is America's, ground-based infrastructure for deploying technology, this type of technology, where you can look at things like, monitor pollution, noise, and traffic. So we started down into this smart city arena, looking at where trust fits there. And I will just note that there were a lot of collaborations that came out of this during this period of time with Argonne National Labs and the Array of Things project, with campus, Georgia Tech campus, and something called vertically integrated projects. So it's a research curriculum that Georgia Tech has. working with the campus and the City of Atlanta. The City of Atlanta, under our previous mayor, was very progressive with respect to smart cities and had designated a smart city corridor that was right by the Georgia Tech campus. And also some kind of national and international organizations. So NIST's Global City Teams Challenge initiative, bringing people from companies and organizations from around the world together on smart city projects, as well as nationally the Metro Lab Consortium, which pairs universities and cities together for smart city projects. So again, I'm down this path, and the organization I work for came back and said, that's very interesting, but what about national security, right, where we typically work? So it was a good opportunity to step back and say, from at least in the US DoD perspective, do they care about Internet of Things? And when I first started this work, it was you were very hard pressed to find anybody in the US DoD that cared about this, right? They said, yes, it's a very interesting problem. Yes, trust is important. No, we haven't thought about it, and so they weren't really interested in funding anything. But what happened over the years is that there's a lot of things popped up, right? Industry 4.0, the industrial Internet of Things, became important for them for manufacturing. Smart bases, or installations of the future. The Army held a workshop, a mad scientist workshop at Georgia Tech a few years ago, looking at how to make bases smarter, how to basically connect bases together to create a more distributed city of sorts. The Army also had a science board summer study looking at the benefits and the risk associated with Internet of Things. So what happens when soldiers, warfighters, are operating in cities, maybe for humanitarian reasons, and they're surrounded by this technology? What does that mean to them? And then also DARPA became interested in this, but from a little bit different slant. So for those of you that not in the U.S., DARPA is an organization within the U.S. that funds defense-related research. And they were interested in what happens at the intersection of smart cities, megacities, which are cities with 10 million or more people, and something called gray zone tactics. And so the short version of gray zone is it's anything but kinetic warfare. So there's no guns, there's no bombs, there's nothing. We're not thinking of military operations in a traditional sense. It's what we're facing today. It is influence operations. It's deep fakes. It is trying to spread misinformation, things like that. So they became very interested in where does trust fit in that space. So that spawned another set of projects, which now looked at the physical layer, the application layer, and finally looking at some simulation aspects. So briefly, those projects. So fog computing, the easiest way to explain this is when computation is pushed all the way to the edge, right? So the sensor array that I mentioned to you that's at the edge, any sensors, computational nodes that are at the edge, how do you actually take advantage of computing in situ instead of sending things back to the cloud and waiting for that delay to get it back, right? So for real-time, time-sensitive situations, decision-making, fog computing is important. And so we did a lot of some work with campus, with faculty on campus, in this space, looking at pedestrian statistics. And our real focus was how kind of the reliability of this technology in degraded networking conditions. Privacy zones, so now jumping from the bottom layer to the top layer of that trust framework, privacy zones was the work that came out of the IISP collaboration, so that Institute for Information Security and Privacy. And so this was really focused on the fact that we know location-based services raise a lot of concerns over privacy, right? And the fact that a lot of the services that are available are very manual and one-size-fits-all. So cloaking, permissions, right? that once you set it, it's there's not many ways that you can personalize that. And so this research was about how to construct personalized fine-grained regions to protect a user's privacy based on things like spatial, temporal, and semantic customization. So the idea that I might want to protect my privacy when I'm at a hospital, I might want to protect my privacy when I'm at work, but I don't really care about protecting my privacy if I'm at the grocery store, right? So how do you customize that in a way that you don't have to constantly change those manual settings, but you can specify what's important to you, and then the system preserves your privacy in those situations based on where you are geographically. And then another project that came out of was this Mad Scientist Conference was, okay, we have all these different little pieces of these projects that we're doing to look at different aspects of trust, but how do you even think about trusting a smart city itself, right? A city that has millions or billions of devices. How do we begin to understand whether we can trust those cities? And so what it turns out, that trust is has an inverse relationship to risk, right? The more risk there is with something, the less we tend to trust it, right? So if we want to know if we can trust smart cities, we need to define risk factors for those cities. And so we came up with 3 different things that had to do with non-technical, where humans are in the loop and managing the process. Technical, so all the sensors and devices and software development. This is where cyber attacks comes in. And complexity, because the reality is that cities are complex, multidimensional interactions between people and technology. And we know that sometimes that relationship between people and technology is fraught for accidents, normal accidents, and things like cascading events. So we came up with this idea of how to create and evaluate risk factors. And then the last work that we did was along that lines of gray zone modeling. So how do you actually model a smart city, model it in layers, think about where the smart city technology comes in, think about how you can use or misuse that technology to influence people, to create distractions in cities, prevent public officials from being able to respond to emergencies, and that type of thing. Okay, so that brings us to the last part of the talk, which is simulation trust, okay? So here I've come and told you about all of this trust work that we have been doing related to the Internet of Things. So an obvious question for me was, does this apply to simulation? So we'll stay on the city theme because that's an easy one to talk about the complexity of systems and technology. And so we know that cities are undergoing revolutionary changes, right? Smart traffic management, autonomous vehicles, smart power grids, cyber threats, climate change, migration, the fact that we're turning into mega cities, crowdsourcing data, on and on, right? Well, it turns out that Richard Fujimoto in his 2014 Titan talk actually put forward a challenge in his presentation, which was we should be able to use M&S to manage the operations of major urban infrastructures, right? So he was proposing, he was kind of seeing into the future there, that the cities were undergoing these great changes, and that where does simulation fit into helping cities with respect to managing and operating all of this infrastructure, and now this technology. And so what he proposed, this is his slide that I stole directly from him, right? So he talked about DDAS, the Dynamic Data-Driven Application Systems, as a way and an example of how real sensor data was being used to drive, or could be used to drive simulation systems for things like prediction, optimization of different systems, calibration, validation of systems, right? And so I was intrigued by that, so I went to see, is DDAS really being used to monitor, control, and predict cities? So I went to the easiest site that I could go to, which was the National Science Foundation, to see what they had been funding in DDAS research. And it turns out that they really did have, there was a lot of DDAS projects that were not related to cities, but there were DDAS projects that are directly related to cities. Like monitoring large-scale structural systems, monitoring urban water distribution systems, and monitoring traffic and transportation systems. So while it may not be a mainstream approach just yet for how simulations are being used to monitor and control cities, it is obvious that it is coming and that there are more opportunities for that, right? So then we start thinking about the trust piece. So we know, right, that simulation models can be used to control, give commands to sensors and actuators, or provide faster than real-time prediction. DDAS is one example of how that occurs. So then that makes us, what does that mean for our modes of operation? So now we can start thinking about where does trust fit into this? And how do you think about simulation and Internet of Things technology together in a similar paradigm? So I just extended the modes of operation from the earlier slide to show that there could be human-to-human interaction where simulations are involved. Human-to-simulation interactions, simulation to simulation, or simulation to machine. So where does trust fit in all of those modes of operation? Okay, so now putting back my hat from this organization I work for, where we think about national defense. And, it occurs to me, right? So are we overplaying this idea that there are cyber risks to cities? And in effect, what does that mean to simulations that might be used in cities? So this is a quote that comes from Major Liu at the Defense Threat Reduction Agency in 2015, where he talks very much about how IoT is going to change, people's lives. The connection that it's going to bring will change how we interact. That it will also, the risk of how it makes people and cities targets. But this whole idea that, in short, cyber is the new weapon of mass destruction threat, right? Especially if we are using this technology in our cities. So it's a little bit of doom and gloom, but it is also just, a nice warning to say we need to think about this. So if the sensors that drive simulations that we're going to use in cities are hacked, could they be used for mischief or something worse? Right? So what happens if the data that's driving transportation simulations made traffic signals stay all red or all green in all directions, that it tweaked electronic speed limit signs, or it sent everybody onto the freeway all at the same time? What would happen, right? We have simulations that may be monitoring and helping manage traffic. What happens if those simulations are not trustworthy? How would cities respond to inadequate supply of electricity or water? Or worse yet, not be notified that drinking water is contaminated? And lastly, what if waste collection was interrupted, especially in the summertime, and garbage piled up in the streets because the data from smart trash cans used to optimize trash routes was misrepresented, right? Some of these would be nuisances. Some of these could be distractions for something else, more dangerous for a city. So then that brings us to, does trust apply to simulations? So here's my push. I would say that I just got through telling you for the most of this talk that trust applies to the Internet of Things. I just told you definitions and architectures and projects that we've done. I started off by saying IoT is just another LVC system, right? So that must mean that trust applies to LVC, and it applies to simulation. So that's my statement or belief. And so now I'm going to give you a couple of examples as I wrap this up. I'm going to go back and take you through all those projects that we did related to trust, and let's see whether we can come up with any application for how they might apply to simulation. So how about the privacy work, right? The privacy zones or that in situ privacy algorithms in the sensor arrays, right? So if we have in live simulations, sensors that are being driven, collecting information from real city environments. The information that those sensors collect, like location, for example, is maybe important as it drives the simulation. But do we need to preserve the privacy of what we collected that location from, right? The specific person, the car, something like that, right? So maybe there is an opportunity for how privacy and things like privacy zones apply to live simulations. For live virtual constructive, all simulations, right, communicate. They pass messages back and forth to communicate information amongst themselves. And so the work that we did in machine-to-machine trust, where those, in our work, the nodes were rating each other. Maybe simulations can rate each other about how trustworthy they are. Or maybe using some form of trust marks to communicate information, which is, a discrete set of well understood and trustworthy information. So for fog computing, this seems to very much apply to the live and constructive types of simulations, right? So when we push computation out to the edge, either for those live devices or for the analytics that we're doing in those devices, which would be constructive, right? So how do we create more trustworthy platforms, reliable platforms, especially in things like the absence of reliable network access? And then the last one is that risk framework that I told you about from the How We Trust Smart Cities. So I added the A in there, so the live virtual constructive and autonomy. Should we have a risk framework that we understand what those risk factors are and how we begin to look? Because as you start to embed simulations along with IoT devices more in cities to make decisions on our behalf, and to route traffic and access and make decisions for real equipment, then we need to know what the risks are associated with that, right? Because simulations that are driven by sensors are susceptible to attacks, to cascading effects, and to normal accidents. Okay, so as I wrap up, I'll say that what do we need a research agenda? I think it's a valid question. I don't know if we need a research agenda, but these are 17 factors that NIST published in a report recently about the technical concerns that negatively affect the ability to trust IoT products and services. Okay, so there's a lot of things on this list that we are already doing research on, right? Things like composability, interoperability, synchronization, testing. There's a lot of things that we are already doing. Is that maybe that research just needs to include some type of trust aspect to it. But there are things here that we don't necessarily typically think about as our research agenda in the simulation community. Things like data integrity of those sensors that are going to be feeding the simulations, or reliability, visibility and discovery, right? So maybe there are opportunities here to help us think about new research in this particular space. And all that doesn't even consider, if we're going to deploy simulations in cities, right, we also need to think about insurability. And risk measurement as more commercial vendors think about their technology, right? So I'll just wrap it up and say I think that I would propose, I think that trust does apply to simulation. I think that there's new opportunities as we start to think about where simulation is going in terms of being used, embedded in real-world systems, being used to make decisions on our behalf. I think simulation has a place there. And I think it just brings or begs the question that there are new areas of research that we need to pursue to ensure simulation trust in these untrusted environments. Thank you for being here.
Thank you for a great talk. Are there any questions? We have mics on both aisles.
Hey, Chair.
Thank you very much for a great talk and for actually proposing a great research agenda. I think we can all go back to our offices and get to work next week. My question has to do with the trust issue that you raise. And I can't help but try to connect this to the tradition issue that we have of validation and model credibility. Could you speak a little bit on what the relationship could be? Could trust research, for example, extend, and be based on that foundation?
Absolutely. So, and I think I mentioned this in the paper, right? We're already doing work in validation, credibility. People, I think that there are a number of organizations, I think I listed in the paper, that are already looking at different parts of this. Trust, they might not call it necessarily trust outright, but it definitely has a relationship here. So I do think, and that's kind of the point of this slide, is that there's a lot of things that we are already doing, validation being one of those that fits very much in the space. So it's not that we aren't tackling this problem, it's, should we expand our thoughts about, how to expand the research space related to things like validation, right? Because if you go back to the original definition from NIST, things like security and reliability and privacy. So in the work that we do in V&V, are we thinking about privacy? That's a good question. Maybe I need to look at the agenda and see if people are presenting papers on that this week. But, where do the traditional work that we do, does it apply to some of these new dimensions that we need to start thinking about?
Any other questions? Well, I've got a question. So, there's an interesting tension, I think, between privacy and trust, right? If I want to trust you, I want to know something about you, which is pushing against your privacy. Similarly, I guess in the data world, people talk about protecting privacy by differential privacy mechanisms. You essentially fuzz up the data,
Yes.
so to make it hard for somebody to infer facts. So that, if you're trying to preserve privacy and transmit data, you're actually undoing a little bit of your reliability. So I was sort of wondering what you think about this tension between trust, efficiency, and privacy.
So this is an area that with the faculty, the College of Computing faculty that we're doing the work on privacy zones, they're actually starting to tackle that, right? And so I wouldn't say that I really have a great answer right now because we're just starting kind of extending that privacy zone and differential privacy and starting to think about its application to simulation and communicating that data. But you raise a great, a great question, that there is a tension there. And I think that in the simulation world, we haven't really thought very much about privacy at all, at least in the literature that I've read. So I think it is a great new space to really think about whether we have solutions to those types of difficult questions.
Any other questions? Well, I think we all have some interesting technical issues to think about. Yeah, privacy and simulation, right? What if you need to both communicate and obscure your results at the same time? So anyway, let's thank Margaret again for a great presentation.
Thank you. And thank you for being here. I appreciate it.